Thank you, Peter. Recording? Great. So today I would present our work on Circular Future Cities, which is a project, a collaboration between ETH and multiple universities in Singapore, and in particular, our work on a material passport ontology at a city level. I would like to acknowledge the contribution of my co-authors, Firehiwot, Kedir. She could not be here today, and Professor Daniel Hall, who is here in the room today. So, what's the premise? We all know that we need to build more to meet the global needs, whether it be the buildings and renovations in the modern or developed countries, or whether it be the more construction, infrastructure, and building that is coming up in the developing countries. But we also need to do that better. We cannot actually contribute to more of global emissions anymore, and our sector is actually responsible for more than 39% of the global emissions. So what's the solution? We need to look at a new kind of method of construction, and most of the research around this time is pointing towards circular economy. You might have seen it from the first two plenary presentations. It's all about reuse. How do we do that in terms of different aspects? And what is circular economy for this presentation? It is about moving away from a linear kind of construction method where we extract materials from our mother earth, then transform into products integrated in our buildings. The buildings go through the life cycle, and at some point we demolish the buildings and we use these components, those simple dust. Sometimes we recycle it, but again it has a lot of energy cost associated with it. Instead, using a circular economy, what we're doing is extracting this material, creating the products which disassemble, which could be used in our later project, and then we assemble it into a building, use it for the life cycle, then disassemble. So basically, when you are reading the component itself, it has all this information about disassembly and all those parameters integrated, and it's also designed for disassembly. So you take it out, you put it in a new building, and the same component will have multiple life cycles, multiple. What do we gain by it? All those embodied carbon on manufacturing this particular component. You're not going to do that again for the next building. You'll be using the same component again. So that's the idea about circular economy in the construction sector. But what we have seen so far is when we are studying circular economy at a building level, most of the studies look at different aspects at a building level, but circular economy itself is much beyond the building level into a systems level. So we are looking at it from a city perspective, but it might be even more broader in a settlement system perspective. So the circular economies in construction depend on systems beyond the building, and particularly on inputs and outputs into the building. So that's where our project on Circular Future Cities is, where we study how to support circular economies in construction at the scale of a city or a settlement system. Our project, Circular Future Cities, adopts a systemic approach to develop integrated framework and tools based on digital technology to inform the design of circular cities. And this is our team. We have 18 members, and it's increasing. So at the moment, I'm not going for each of the members, but what we need to see is this is a team of civil and environmental engineers, material scientists, architects, urban designers, computer scientists, etc., who are working collaboratively. And we are looking at the circular economy from different perspectives. And we have a lot of data that's coming into our project, and these data has to be integrated. That's where we need an information management framework. So the information management framework that we are looking at should support the flow of materials. It should ensure the quality of information supporting these materials. It should ensure longevity of the data because it's being used for more than one life cycle. And also, we need to have all the material characteristics. So that's where this particular paper comes in. So everyone might ask, why don't we use a centralized storage where we put all the data in? But for a circular kind of construction, we need to look at the longevity of the data, which is more than multiple life cycle of a building. That means more than 100 years. So are you sure that all the platforms would be existent then? The second thing is everybody would like to own the data, especially in construction. The ownership is always a hot question. So can we ensure that everybody owns their own data and they can control the access to the data, choose the service providers, choose who controls the data, etc., while ensuring provenance of the data and not being vendor locked. So this is why we are looking at an ontology perspective or looking at a semantic web perspective into this one. Coming to the objective of the paper, so we have developed an ontology, but it's not in the paper yet because it got developed a little bit after, so you will get a sneak peek into the ontology. But what we would be providing is the directions on how do we integrate existing ontologies to create our realize our need. So that's what the paper is about, and the method we used is based on the Graniger method on first identifying the scope and purpose, intended users of the ontology, then from there developing the requirements, reviewing the domain knowledge, and using existing ontologies, then integrating the ontology, testing it, and scaling it up. So in this paper, we would go through the first 3 steps. That's like I would talk about the scope, purpose, and intended users. Then what are the requirements and which all ontologies have we surveyed and why we choose those. So for the scope, we have like mainly the first thing, that is conceptualization of building stock information. So at a city level, we need to understand what materials are available in the city. So basically, we need to look at a city level, draw a boundary around it, then understand what all buildings are there in the city or what all infrastructure is there in the city, then go into the building level and looking at like what are the different spaces, what components are there in that particular building, then go into particular component and understand like what materials are made up of the component, or is it the component is an assembly or not, and go down. Now, that's just the traversal of information or search. And once we get to the material level, we need to understand the material properties such as physical and functional properties in there. The last, we also need to make sure that whenever this material is like taken into a new building or a new structure, sometimes it might be cut. So if it is a timber beam, from Brandon's example today morning from the building in Geneva, it got cut into different pieces to suit the dome. But we still need to maintain the provenance of the previous structure to understand where it comes from. So that's another thing that we need to look at. So essentially what we are doing here is creating a database or kind of like a network of data of materials in a city, then joining it together using a topology in such a way that it could be searchable and retrievable. And in future, what we think is like if a kind of a contractor was looking for like a particular type of steel that would be required for a project starting like 2 years from now or something, we should be able to provide details about where he or she could find it from. So this is our vision, and there's a lot of like hanging pieces around it, which is what we will be talking about. So we have like 3 different scenarios kept as like competency questions. Is like the first one is like, when will double glazed windows with a particular kind of dimensions be available in city? So if I'm an architect trying to design a building, I have this particular dimensions and the idea, but I don't know where it could come from, so I would be querying this database. At the moment, how it works is based on networks. So if you are a contractor, you have like networks with like demolition companies, etc. So if you have the network, you would get it. But what we're looking at here is like, can we automate that process, just like a Tinder match for materials? So basically, in order to do that, we need to have like 2 levels of understanding. The first one is the kind of like schema level understanding. Like there should be a city, there should be a building should have a component which should essentially have like properties, etc. And on the schema, there would be like data instantiation. Like here, the city is like city XX, and building in that city, there's like a building XYZ, which has a window, which has a property of glazed. So we need to have this kind of information. And the idea is like this particular abstraction, this is just an example, could fit into many terms, many places. And if I look at it, I could build an ontology just for this one. But would that cover everything? I wouldn't think so, because there's a lot of detail for each of these things that would come in. And like if you look at the community here, there's a lot of like detailed kind of like ontologies for different components that have already been created. So this paper is about whether can we integrate those ontologies and still find meaningful information through semantic queries. So from our literature search, we've identified these 7 kind of parameters or 7 kind of requirements that we need in an ontology. First, we need the topology. That is, we need to go from a city level to the building level to the space level to the component level to the last asset level, and vice versa. Then we need to know the actors who can read and write the information. The actors could be humans, and it could also be machine agents, which are programmed to input and take out information from this. Then we should always need a geometry. Geometry could be of different representation. This is essential for calculating the quantity of the materials or something that is available. We need to have the material properties, of course, and we need to also capture the property evolution, because over the life cycle the property changes, and we need to capture that evolution of the property over the life cycle, and that should be also in the kind of the passport or material passport, because that material passport is what everybody would be looking at when they are actually integrating this component into a new building. That would contain everything related to the history. Just like how you travel from a place to place using a passport, and somebody can look at it and see where you've been, or your car's maintenance record. So if you're buying a second-hand car, you look at the maintenance record and see what has been this car subjected to. Is this good enough? Has it been involved in a big crash? Similarly, we need to know what has been this particular material been subjected to. And then we also need to know the life cycle. That is the life cycle of the building, life cycle of the component, and at what stage it is, and we need to know what went into it. Finally, we also need to look at the semantics for circular exchange. That is when one of the component is removed from one place and put it in another place, it might be split it into 2. So there are certain kind of semantics associated with it, which needs to be there if you want to traverse the data. So these are all the requirements. And how do we actually integrate it? As I told, existing ontologies has already codified in-depth domain knowledge. So we should make the best of it. And during my research, I've been talking to different stakeholders, and when they were asking, okay, this needs multiple layers of information in it, and whether your ontology has it. If I had created that ontology, it wouldn't have. But when I reuse ontology, I could, with diagram, show this ontology could handle this kind of levels of information. I would go to that example later. And there are 2 ways which we could actually look at it. We could assemble and extend existing ontologies, or you could merge different ontologies based on the similar. So we went for the middle one. We assembled and sometimes extended the ontology. So the extensions were not semantically adding more information to it, but the extensions were just to reduce the complexity of the SparkQL queries that we were trying to do. So we could write easier queries with our kind of extensions, but the data is actually instantiated in the existing ontologies. So I would just go through a list of ontologies that we looked at. For lifecycle, we looked at the digital construction information ontology. So just before going on to this, we selected these ontologies mainly because they have the similar kind of upper level ontology, which was the BFO ontology. So the good part about that is it would be easier to integrate rather than some list of random ontologies, and we cannot integrate it together. So the first one is digital construction information ontology, and we took the lifecycle piece of it. So the good part about it is it has all this lifecycle stages, which is called BLS stages, which could be integrated into the product or even at the building stage. For the actors, again, we use the same digital, it's a similar digital construction information ontology, and use the actors agents part of it. So here the good part is the agents could be humans or even computer programs, as long as we have the semantic understanding of it and we could actually integrate it. For the topology, we started first from the city level, then to the building, then to the part level. At the city level, we use the OntoCityGML, which is based on the CityGML. So we could have the queries onto whether a building exists, where is it, what are the kind of things associated with it, etc. So this is again developed part of the Circular Future Cities project on a different kind of title called Cities Knowledge Graphs. So they are literally semantically encoding all of this into a triple store. So we could actually reuse their ontology. The second ontology at the building level, for the topology, we used obviously the building topology ontology bot. Peter is here, and a lot of people who are here might have already worked with it. So the idea is like from the city level, we get the building level. From the building level with bot ontology, we can go from like the space building level, then to the story, then to the space, and then to kind of like the building element. So the element, from the element level onwards, we would go to a detailed ontology, which is again the building product ontology. So here we could actually again kind of like expand on the product into different kind of like things of assembly or all the way to a component to which we could assign the material property. For the material property, we use material property is coming, but like when we reach the component level or that asset level, we need to have the geometry so that we can compute the material quantities out of it. So that because there's, as you have seen, like there are multiple ways of collecting the data, we need to actually include all this. So we use the ontology for managing geometry, which is the OMG ontology. And the good thing about that is like it has a geometry state and also different kinds of like geometry description. So it could be a very kind of like a basic description for LOD1 display, or it could be like a high level detail for better visualization. So it could always be integrated in the same ontology. Finally, the material properties. So here we again looked at from the digital construction information ontology, we took out the materials part of it. It has a lot of information on physical chemical properties and how the materials are constituted like in a kind of a particular component. Then, as I said, we also need to keep track of the property evolution. So we use the OPM ontology, which is the ontology for property management. So what it does is like it preserves the states, different states of like material properties, or which could again go like we could trace back, and we could keep like a current state based on what is happening now. But we could also go back to a previous state. We could restore a state to the current state, etc. So that's why we use this particular ontology. And finally, for the semantics for circular exchange, we try to integrate the circular exchange ontology at the product level. So it helps to actually have input, which is basically the component which is going to be reused, then give us two outputs, and we could actually preserve the logical chain here. And also like all the ideas about creation, post-use, reverse logistics, etc. is handled through the circular exchange ontology. What was the result? We kind of like built it up, and we have like an ontology together. And where you can see all these colors, except for I think one or two of the CFC ontology, it's all the existing ontology. And as I said, like we put the CFC ontology mostly for reducing the complexity of queries going through like different levels. But essentially the data is actually stored in these ones. So whenever like it's not in a vendor log schema, it has enough amount of data. So when you are viewing it from different perspective, you have all the data you need. But when you are doing the query, you just have like access to the limited amount of like data. And the second thing is like, because we have the CFC kind of like representation, it is also helping us aggregate the data. So when we are what we are trying to envision with this kind of like ontology is to create a decentralized marketplace. So the data itself has value. So we will have like a public version of the data and the private version. Private version would be behind a paywall, which is incentivizing the people who put in the data. So the queries would actually automatically aggregate the data from the private servers onto the public one. So that's how we envision the decentralized marketplace with, I'm not sure whether you can see my mouse, probably now. Yeah, so there's a public server, everything in green is like public, so it aggregates the data from the kind of like secure servers, and at the public level, what we do is only helping the searching of the data, but to get the detailed information, you would have to pay for it. So this incentivizes people who put in the data, and there's kind of like a monetary benefit or other kind of benefit for people to actually maintain the data. Otherwise, it would go lost. So in conclusion, what we have done in this paper is we have given the directions to develop a material passport ontology at a city level to enable circular economy. We identified the requirements for the ontology and also kind of like the end users who might be using it. And we have also provided recommendations to integrate existing ontologies such as ontocity GML, BOT, BPO, OPM, CU, DIC, and OMG to provide this, to develop this material passport. What we are trying to do with this project, again, recap, is going from an urban mining paradigm, which is basically looking at just like a mining, where you don't exactly know what you might find in a mine, but you have a broad idea, to coming with the urban harvesting, where we have more predictability on what data or what materials you can harvest from a city for the future buildings. So that's our aim with the Circular Future Cities project. It's time for questions. If you have any, thank you for listening to the presentation.